Good afternoon. Can you hear me okay in the back? I'm used to asking this question when I'm teaching the first years in this room. So if you can hear me, thank you. Thank you, Professor Wilson. All right, so I want to wish a good afternoon to faculty, students, postdoctoral fellows, research associates, and staff of the Department of Physics. And good afternoon to those of you in the broader University of Toronto community and beyond who are with us today, either in person or joining us online. Today, I'd like to invite all of you, whatever your origin, to consider yourselves members of the Department of Physics at the University of Toronto. My name is Paul Kushner, and I have the privilege of serving as chair of this fantastic department. In that role, I'd like to extend a very warm welcome to the 2025 Welsh Lectures in Physics. Out of curiosity, how many of you are attending the Welsh Lectures for the first time today? That's a very nice show of hands, and I just want to welcome all of you, and especially warm welcome to all of you newcomers as well. As I extend words of welcome to you, I'd also like to share with you the official University of Toronto Statement of Acknowledgement of Traditional Lands. So I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still the home to many Indigenous peoples from across Turtle Island, and we're grateful to have the opportunity to work here on this land. So since 1975, we've been holding the Welsh Lectures in celebration of the legacy of the late Professor Harry Welsh, 1910 to 1984. Each year, we invite two physicists at the leading edge of the discipline to share their expert perspective on cutting-edge topics. Today, you'll hear about their tremendous work framed at a high level and intended for a broad public audience. And tomorrow, the series will continue with two colloquia that focus on topics of their current research. You're going to hear more about the speakers shortly, but what about Professor Welsh? He was a fellow of the Royal Society, a distinguished molecular spectroscopist, a child of the department in his undergraduate years and some of his graduate studies as well, professor in the department starting in the 1940s, and chair of the department in the 1960s. I'd say in some important respects, this is Harry Welsh's department. He presided over the department through its move in the 1960s into the newly constructed McLennan Physical Laboratories, which we still occupy today. And he established our modern department through disciplinary broadening and tremendous growth. He doubled the size of our faculty, more or less, under his watch. Just as an aside, and speaking of growth in our department, I'd like to take this chance to introduce two new colleagues who joined the department's faculty since the last Welsh Lectures in 2024. The first is Professor Matthew Robbins. It's up there, okay. He's an assistant professor teaching stream who's jumped into his role as instructor since his arrival in August of 2024. Matthew, I think it's worth highlighting that this was actually Harry Welsh's role in the department through the years of the Second World War, when he served as lab instructor and lecturer in military training programs here at the university before joining the faculty. Second person who isn't with us here in person today is Professor Jonathan or Yoni Khan. He's a theoretical physicist in the area of high-energy particle physics and artificial intelligence, who's been setting up his busy research program since his arrival in December 2024. So I want to just extend a warm welcome to our two new colleagues in the department for this year. So now to the business at hand. It's a great honor for us to host two wonderful guests whom the session chairs will be introducing properly. Professor Kumran Vafa, the Hollis Professor of Mathematics and Natural Philosophy and the chair of the physics department at Harvard University, fellow chair over there, and a leading authority, as you'll hear, in the area of string theory. And Professor Pablo Jarillo, the Cecil and Ida Green Professor of Physics at MIT, an experimental condensed matter physicist driving the forefront of research in novel two-dimensional materials. Before we, pass the podium over, I just want to, in advance, thank the Welsh Lecture Committee. And I'm going to leave the proper thanks to Professor Youngbeck Kim, who's going to talk a little bit more about the committee's work. But on behalf of the department, I'd like to thank Professor Kim for leading this effort this year. So let's give him a quick round of applause. One last word, it relates to the festivities. So after the two lectures, a reception will follow the lectures around 4:30 p.m. in the McLennan Physics Undergrad Lounge. This is MP 125, so just follow the crowd back. And please feel welcome to join us for the reception afterwards. And now I'd like to hand the mic over to Professor A.W. Peat to introduce our first speaker. Over to you.
Hello, can you hear me okay at the back? Sweet. Good afternoon. My name is A.W. Peat, and I'm a physics professor and string theorist in the Department of Physics here at the University of Toronto's St. George campus. It's a tremendous honor to even share a stage with somebody so accomplished as our first Welsh lecturer for this afternoon, Professor Cymran Baffa. As you can see from your program, Professor Baffa is a highly decorated theoretical physicist. He's had a long list of awards that he's won, including the 2008 Dirac Medal from the ICTP, the 2017 Breakthrough Prize in Fundamental Physics, and the Mustafa Prize in 2021. I'll confine my additional remarks to just a few facts that a general audience member might not know, because I feel that really lengthy introductions just eat up time that the speaker could have spent on explaining physics, which is actually why we're all here today. So in our field of string theory, the primary major international conference is known rather imaginatively as the Strings Series. It has been held every year since 1995 in a variety of countries around the world. I'm one of a few people who have co-organized more than one of them. The first of them was 98 in Santa Barbara, and Strings 2005 we held right here at the University of Toronto. That was the first time it had been held in Canada. Professor Baffa is one of the 10 most highly invited speakers of all time at Strings conferences, having spoken at 16 of the last 30 of them by the count that I managed to find online. He's presented on a wide variety of topics, including superstrings, physics beyond perturbation theory, topological strings, quantum foam and black holes, F-theory, superconformal field theories, and most comprehensively, the superstring landscape and the swampland, and making connections with astroparticle phenomenology. This and other technical evidence illustrates the fact that he's a world leader driving development of new techniques in string theory and mathematical physics, the head in the cloud stuff, and also a world leader driving development of our theoretical understanding of experimental particle physics and cosmology, or the feet on the ground stuff. My own first non-trivial interaction with Professor Baffa was a bit of a whirlwind. At the time, in January 96, I was a young postdoc working at the Princeton Physics Department in the midst of a lot of activity after the recent discovery of superstring dualities in the physics of D-branes. He was visiting the Institute for Advanced Study at Princeton to give a seminar about his now world-famous discovery with his Harvard colleague, Professor Andrew Strominger, of calculating the Bekenstein-Hawking entropy of particular black holes in 5 dimensions from first principles. And they'd got the right result for the black hole entropy with no fudge factors. And I remember being absolutely bowled over by it and stayed really eagerly after the talk to ask some extra questions, despite my fairly huge social anxiety. He mentioned casually that he actually knew the answer for the rotating case as well, but at the time, the black hole solutions were not known. I just mentioned casually to him that I knew how to make them, and a week later we'd written a paper about it, which is actually the fastest I've ever written a paper in my life before or since. So that's just an idea, give you a little idea of just how creative he is, both in his own research group and in terms of stimulating research of others. He's also a very highly cited physicist. If you check on inspirehep.net, a comprehensive database in high-energy physics, he has over 76,000 citations for his 348 papers, which is a pretty astonishing degree of impact for somebody working in string theory. So I invite you to listen to his presentation with intellectual humility and eagerness, because you're about to learn a bunch of exciting new things and be blown away by his brilliance at both research and teaching. Please put your hands together and help me welcome Professor Cymran Baffa.
Thank you. Thank you for such a kind introduction. I'm not sure I deserve so many accolades, but thank you very much. It's a great pleasure to be here and tell you about the subject, which is my favorite one, string theory. See if this works. Doesn't work. If this is going to work now, no. Okay, so string theory has been a subject that physicists have worked on for over 50 years. And, continuing, people are still working on it. And so why are we doing this? Well, because we think it actually is a fundamental theory of nature, and it unifies microscopic phenomena, which is represented by quantum mechanics, which quantum mechanics deals with macroscopic, large-scale phenomena. The biggest one being the whole cosmos and all the galaxies and all that, which is described by Einstein's theory of general relativity. So from the smallest to the biggest, we want to kind of put them together, and string theory has somehow managed to do this. Indeed, there has been a lot of conflicts generally between trying to do that over many decades, and it has been a big struggle for physicists to do this. The idea is rather, in some sense, simple, but it's just the following simple idea. You replace point particles, entities that look like the atoms or electrons and so forth, much smaller, just like points. Replace them by extended objects like loops of energy, which we call strings. Now, why is this a good idea? It's not obvious. Why should you do this? But somehow this thing has solved the problem of reconciling the description of the Einstein's theory, which is good at very large distances, to something which should happen at very short distances to resolve conflicts between these two different descriptions. So that's why we think it works, and we think we are excited about it, but it's a bit unexpected that you had to do this for it to work. Now, it is too early to give you the final theory right in front of you to spell it out. We still are in the midst of discovering string theory. It is work in progress. Okay, so what am I doing here? We haven't finished the subject, so I should go back to work. Well, that's a good idea maybe, but surprisingly, you can ask me, what have we been doing for the past 50 plus years? And why is this not finished? What is going on? So let me say at least status report. Let's look at it that way. We have learned a few things, many things, I would say, and I will try to explain some of these by looking at things we can do. So this is the thing that you have a lamppost, you look whatever you can see under the lamppost. So that's what we have been doing, trying to understand it. And you might think, well, this is a limited knowledge, perhaps. What is surprising, and this is what I hope to convey, is we have learned a huge amount of unexpected things already just by looking at this, what one might call this lamppost effect, that looking under this very limited lamppost. The principles are astonishing, what we have learned. So these principles are counterintuitive, and I will try to explain some of these new principles using some examples to illustrate it. Perhaps to put things in perspective, it might be useful to give some historical lessons. In fact, many developments in physics historically have relied on giving up what you believed in very strongly. Something which was solidly established had to be questioned. So let's go over a few examples of this. The Greek had already discovered, they're very smart, they had discovered that the Earth is round. And they were debating, why is the Earth not moving? You know, they were looking at the sky and they were seeing the stars are moving, this, you know, the star, meaning the planets are moving, the sun seems to be moving, the moon is moving, everybody's moving, and the Earth isn't moving. Why wasn't the Earth moving? That was their question. So they had figured out it's a sphere. They were enamored with geometry. They thought, if the sphere is, if the Earth is at the center of the universe, then anywhere it goes, it misses being at the center. So being at the symmetric point, it therefore is a preferred situation, and therefore it doesn't want to move. Okay? So they tried to explain by symmetry principles why the Earth doesn't move. Now, their use of symmetry principle continues to date in physics. They're trying to prove the Earth doesn't move. Well, that didn't quite work out, but the idea that they were trying to do, namely using ideas of symmetry to try to explain physical phenomena, is still going on. But actually, they were smarter than that. Even back then, Aristotle did not accept this argument. He said symmetry is not necessarily a good place to be, symmetric points. And people asked why, and then he gave the following example. He said, well, suppose, so let's see where we go. I already mentioned this. So you go, I think this sometimes doesn't click when okay. So maybe I should stand right here. So he said, suppose we have a circle, perfectly symmetric, and you put a donkey in the middle, and you put some hay around the circle. What's going to happen? Well, do you think the donkey is going to stay at the center of the circle just because of the symmetric point? Even the donkey knows that to survive, they have to move, break the symmetry, and go to the corner, one of the points on that circle, and get the food. This idea is the modern idea of what we call spontaneous symmetry breaking, but I guess Aristotle already knew about it back then. So they had already discovered these very sophisticated ideas, symmetry and not using symmetries, or what they mean or how they break them. Anyhow, to make it short, they figured out that Earth is not at the center of the universe. As we learn more about the physics, we gave up that point. But other things had to come down too. For example, we had this notion of absolute time. You know, time is very rigid. Everybody thinks about it. You know, clock, tick, tick, tick. Everybody. But somehow, this fellow didn't like that idea, and absolute time doesn't exist. Einstein showed through his theory of relativity, this is not true either. The absolute notion of a state of a system, that also fell through when we learned more about quantum mechanics. In fact, now we are celebrating the 100th year of quantum mechanics. We learned that even the notion of where things are and how fast they are moving cannot be stated the way we naively think. So principles change. Now, string theory also calls for radical changes of our understanding of fundamentals of physics. And in some sense, it's reminiscent of the early days of quantum mechanics. It's like early days where, you know, they are beginning to see that some things are not quite working, and they are thinking that waves must be involved in this new description. Like de Broglie has figured out that some wave-particle duality might exist. But it was before, you know, Heisenberg and Schrödinger put the actual equations and things that actually were now exactly what it meant. Actually, we still don't know exactly what it meant there, but at least we had a working principle. We are not there yet in string theory. But I would say we are more at the stage of passing what de Broglie had done. So we are in that stage where we are getting the glimpses of this final theory. And as I mentioned, my aim here today is to just give you some highlights of some principles we have learned about quantum gravity by studying string theory. Let me first summarize one important lesson that we have learned. And this is probably the overarching lesson, is that short distance physics, what happens at short distances, and what happens at long distances, even though they are far apart, they look far apart, they're intimately connected. You cannot ignore the short distance if you want to have a correct description at long distance. This description, this connection between short and long is very surprising. So for example, if you look at, look at this table, you say I kind of have a simple description of it. You don't need to know the details of the atoms and so forth. You just have some general features of its rigidity maybe, and so some basic features of it, you can describe it. But it turns out that if you think about macroscopic things that are allowed, you might get the wrong answer if you do not take into account what the short distance is in the context of quantum theory of gravity. And that's the major lesson that we have learned. So this means that the notion of what we call the effective field theories, that you can describe the long distance by ignoring the short distance by and large, is not working in the context of quantum gravity. And what is the driver of this connection? What connects the short distance with large distance are these enigmatic black holes. These guys, black holes, run the show in this context. They are both enigmatic and also the link between connecting this short distance and long distance together. So this very, they play a crucial role, not just because they look cool or everything falls into it is hard to get out, and that's which captures imagination, but actually they're objects which theoretically make a big link between what's going on at the shortest distances with what's going on at the longest distance scales. So why are they? So let me explain why are the black holes in this way connecting what's going on at short distance and long distance. Black holes themselves can be huge. Some of them can be as big as the solar system. The ones in the centers of galaxy can be that big. So it's big objects. So this is macroscopic physics for sure. On the other hand, they seem to be describing the number of particles or energies that number of particles that they can have at a given energy, which is huge. So if you ask how many particles we have at low energy, well, you measure, electron, atoms, and this and that. But you can say, what if I go to a higher and higher and higher and higher energy? Are there particles with very, very high mass? Super high mass, what about those? It turns out that if you get to a particle of the mass of the whole black hole, the answer we already know through black hole physics. So in other words, for the very, very big objects, it turns out the number of degrees of freedom, the analog of the counting of the number of particles, is related to the area of the black hole. That's remarkable. So it's relating counting of very massive particles, which you might think we don't know anything about, to something very concrete, a geometrical fact, the area of a black hole. That's remarkable. So this is connecting the entropy of a black hole of mass m to the area of the black hole of mass m divided by 4 in the fundamental units of physics. In other words, something at ultraviolet or high energy, which is high mass, is getting connected to the area, which is long distance, or what we call infrared. There's another example of connecting the ultraviolet, short distance and long distance. Suppose you want to figure out what's going on, how many particles there are, and what's going to happen at different energy scales. You take two particles, maybe a particle and an antiparticle, and shoot them at each other at a high energy. If you do shoot them at each other at high energy, they can annihilate each other, but then they can produce whatever they had energy to some other particle. So they can create new particles. So that's one way you can create new particles. Smashing particles, antiparticles, as you increase the energy, you can create higher and higher massive objects. So what are we going to do? What are we going to get? Well, if the energies that you're scattering them at is in what we call the giga electron volts, GeV, you can create protons. Proton, antiproton, and so forth, you can in principle create them. If you go to energies of the scale of tera electron volts, 10 to the 9 electron volts, you can create things like Higgs particle, W particle, and so forth. These are particles which are related to weak interaction, radioactivity effects, and so forth. So you can create all these new particles. But what if you go to a very high energy scales, the energy scale called the Planck scale, which is one of these high energies, or even above that? What's going to happen if you get these accelerators shooting at each other at a very, very high energy? Well, you say, well, that's going to be very hard to do because, first of all, we cannot build such a thing so easily. The energies are hard to get that much. We're still at the 10 TeV regime right now in terms of accelerator, and this is far above it by a huge factor. So this is roughly like 10 to the 18 GeV already. So it's a much higher than the GeV scale. And I'm saying go past that to much higher energies. What's going to happen? Well, it turns out we know the answer. What's going to happen is that you create black holes. So the answer is known. And then what's going to happen? Well, the black hole is going to evaporate. How? Well, by a physics which Hawking discovered using Bekenstein's suggestion that it radiates light particles out at a rate that you can actually predict using large distance physics. So the answer to a very high energy process gets related to a computation which can be done using very simple classical large distance physics. This link shows exactly these surprises that quantum gravity has in store for us. So the answer to what happens in the ultraviolet, very high energies, we just get big black holes, and the answer of it we know. So we may not know the answer to about Planck, but above it, we already know the answer. So we don't have to spend too much money anymore on building accelerators. We already know the answer after a while. We just have to go only up to here. Now, we can ask questions like, are there finite or infinitely many possible would-be universes or solutions to string theory? Now, you could ask, what does that mean? Well, we think we have a consistent theory because we exist by definition, and we have certain number of particles and forces and all that. Somebody might ask, what if I want to have a different number of particles, different masses? Can that be arranged? Well, in principle, you can write a physical theory which looks like it has different number of particles. Is there a problem? Can there be infinitely many possibilities of would-be universes, even though it may not be our universe, maybe somebody else's universe? So are there finite number or infinitely many possible consistent universes? That's the question. The answer is no, there are not infinitely many of them. There are a finite number of possible universes. It turns out because of gravity, there are finite. If you ignore the force of gravity, you could have infinitely many consistent would-be universes. It is the force of gravity which changes the story to a finite set. So it dramatically impacts how we think about physics, namely, the possibilities are also limited. Another fact is that in the quantum theory of gravity, there are no global symmetries. What do I mean by global symmetries? Well, suppose you want to count some kind of particles, like you say I have electron or electric charge. You say, well, electric charge you can count or measure, and the net electric charge doesn't change. You can add or subtract and so forth. But if you take a closed system, the electric charge is conserved. That's what we call global symmetry, the conservation of charge. It turns out quantum gravity says that can happen only if the objects you're talking about emanate electric or magnetic fields, just like electron does, or if you have a magnetic monopole, that would do. But without emanating electrical fields, or what we call gauge fields, you would not have this symmetry, something which is not at all obvious. Why? Quantum gravity is unique. Now, I told you already, the answer to this question, I answered that there could be more than one universe. There are more than one solution, but the set is finite. So that we already said. but are they isolated or not? It turns out that even though the set is finite, they are not isolated. They can be connected to one another. So any would-be solution of quantum gravity could be connected to any other one. Suppose somebody says, you know, I don't like the fact that we have one electron. I really like two electrons. And suppose that ended up being among that finite set that's allowed, let's say. Then, in principle, the principles of string theory suggest that you can have a region in your universe you can create in principle. I'm not saying it's technologically today practical, to create a universe that inside there you will have, instead of one electron, two electron types. So in other words, you can physically create conditions to go to the other quantum gravity that you want. So the universe of possibilities are connected. So there's only one theory, one universe in that sense. You can go from one phase to another, inside the bubble or outside it, and so forth. Then your theory changes. So in that sense, we have a unique theory that we're talking about. The other principle is the weakness of gravity. So I told you that there's more than one universe. And the question is whether or not gravity, just like in our universe, is the weakest force. Is that always the weakest force? So what do I mean by the gravity as the weakest force? Well, you take electrons, for instance, take two electrons, put them next to each other. There's an electric repulsion between them because of the electric charge they carry. They have the same sign, so they repel, but they have gravitational attraction, so they attract. It turns out the gravity, that the force of gravity between them that attracts them is much weaker than the electric repulsion by a huge factor. So that turns out to be true for the elementary charged objects in our universe. The gravity is much weaker than the electric forces between them. So gravity is the weakest force in our universe. It turns out that in any conceivable universe that you could get, which is consistent with gravity, that's the case. Gravity is always the weakest force. So if you said, you know what, I want to have a situation that my electron has such a small charge that if you put two electrons next to each other, they get attracted despite the fact that they have a repulsion, electric repulsion, because I've made their charge smaller. That's a no-no. That's not allowed in a consistent theory of gravity. Not just in our universe, in no universe that's consistent. So we are learning these principles, what is generally true regardless. These ideas that I'm giving you examples of are deduced by using one of the remarkable features of string theory, which is called dualities. What is dualities? Consider a physical theory. You have, particles with masses, charges, and so forth. You might ask, can I vary the masses or charges a little bit, this or that? And in the context of string theory, that can be arranged by certain changes of the parameters in your theory. So you can move in the parameter space. So if you denote the parameters, so here I'm drawing this space as if they are the parameter spaces of my theory. And suppose I want to change these parameters. It turns out that when you do this, when you have these different choices of backgrounds and solutions in string theory, you can start with a given parameter choice and move around to different points of the parameter space. And you get to these corners, as I'm drawing over there. And in these extreme corners, you get a totally different descriptions of what you thought that physics is. In other words, the physics that you start, let's say here, by the time you get to that other corner, look totally different. In this language, we say these two theories are dual to each other. Namely, they can be connected continuously to one another, but they look totally unbelievably different. So you would not recognize that you're talking about the same theory. So, in this case, I'm drawing 6 of them. So these 6 theories will actually be related just by moving in parameter space. These boundary points are kind of like what we call reference frames or duality frames, where the descriptions of physics simplifies. When you go to these boundary theories, there's a simple description of the theory, and we can describe them easily. And they are weakly coupled. Namely, when you try to do calculations in them using physical systems, physical theories give you good answers. So these are under control. So you have these nice pictures which have a classical description. But by the time you come to the middle of the parameter space, the classical pictures break down, and it's very hard to have a simple description. And it's kind of like one classical picture gradually morphs to another one. It's like, suppose you think about it like this. Suppose you want to morph, I don't know, a car to a book, okay? You can take a picture of the car and then gradually morph it to a book. At the beginning and at the end, the things look recognizable, but in the middle, it looks like a very crazy looking object. This is what happens also in string theory. That is, you start something like a car in one corner, you change the parameters, and that gradually changes structure and function and properties. And by the time you get to the shape of a book or a property of a book, you're very far away. And that's the kind of a duality. So somehow the book and the car look very different, but actually in some sense, they're part of the same theory. It's very bizarre. So an example of it is perhaps more familiar. So let me explain this, which is something which we know in the context of, fluids or basically matter. Here, for example, it's the phase diagram. You could think about this as a typical phase diagram one has, where you vary the temperature and pressure on the axes, and you can have different phases, solid, liquid, gas, no problem. So you know what the gas is, the liquid phases, and solid, you can easily describe them. But they look very different, of course. A gas and a liquid look very different. However, sometimes you can kind of be surprised that you can have a path going from a gas phase to the liquid phase without actually knowing when you passed any transition, because you can avoid any phase transition. So the notion that you're in the gas phase or a liquid phase is not a notion you can actually rigorously define. Because just by following this path, there's no particular phase transition. So these lines are phase transition lines, and so here we are avoiding them. So therefore, you have a description which is kind of continuous. This is what's happening in these duality descriptions. It's somewhat like this drawing of Escher, where in one corner or the other corner, you have a totally different story going on. Here you have, black birds flying in the day, and here you have white birds flying in the night. Of course, here the birds morph into the sky, and the white birds on the other side morph into the day sky. And going up and down, it morphs into the pictures of the landscape that are down here. So it's a totally different thing, but they all fit into one consistent looking frame. And that's what happens in the context of string theory. So this is really the most accurate, I would say, description of what we have actually discovered in the context of string theory. This is a very accurate description of what we're discovering. Now, there are some opposite corners of this. When I told you go from one corner to another, what is happening? What are the examples? For example, what appears to be a weakly interacting things, objects which are weakly coupled, weakly interact with each other, become strongly interacting on the other side, but there's a change of frame on the other side, which make them look weakly interacting in terms of new different fundamental entities. So the entity's nature changes. So this is what we call strong weak duality. And then another example is that you go from weak coupling to strong coupling, and you find that extra dimensions open up in this space. We find that sometimes you take a big space and small space, they become equivalent. Totally crazy things from the viewpoint of ordinary intuition we have. How could a small space be equivalent to a big space? It's what's called the T-duality. And another example is that if you take systems which have a lot of ingredients, what we call large N quantum field theories, if you have a lot of them, when you put them together, then you somehow get one extra dimension in which the gravity propagates in. Again, very crazy. So we are having a lot of different phenomena captured by these duality features. Among these dualities, what have we learned using these principles? We have learned something about what is the basic building blocks of matter or lack thereof. So what do I mean by that? Question is, what are the basic building blocks of matter? Could they be, do they have to be, can they be just particles? I already alluded to this at the beginning of my talk when I said in string theory, particles are replaced by loops of energy strings. So it's not point-like anymore. But actually, we have learned that not only that, the string itself could be a membrane. So they are extended objects. It's not a point-like, just like what we thought about atoms. If you deleted these objects from your theory becomes inconsistent. You have to have these extended objects. So it's a necessity for the theory to make sense. So you have even membranes or cube branes or whatever you want to call them, these higher dimensional brains arise. Where membranes, which we now call just brains because membranes are only two-dimensional, you can have branes of different dimensionality, and some of them ending on each other, like this picture denotes. Or like in here, you have these branes which strings stretch from one to the other. These end up describing gauge forces for us. So these objects are all connected and interplaying with each other. And when you change parameters, they morph to each other. Like one dimension of these branes go to a different dimension. The string becomes a membrane, all these things. So the idea of the morphing is a very typical situation that we're encountering. Now you can ask, is there an absolute notion of compositeness? So the building blocks of matter we usually call fundamental entities, but can that notion be itself invariant? Can that be made precise? It turns out that in principle, in physics, when we do this in particle physics, we have this notion of elementary and particle being elementary or composite. But it turns out that this depends on which duality frame you're at, which corner you start with. The notion of fundamental versus composite is not fundamental. So an example of it is monopoles. So in our universe, if we found a monopole, we think about this as a very massive composite objects made of gauge fields and so on, which are excited. We don't think of it as a fundamental particle. So you will have this configuration of particles like this. Gauge fields which behave like a lump of energy source somewhere, which somehow has a magnetic charge. That, if we found one, which we haven't found yet, would have been a composite object. However, we know that even in our theory, if we change the electric charge to a very strong value, if the electric charge could be varied and made strong, it turns out that this object becomes a fundamental particle itself. Becomes light and fundamental instead of being composite and heavy. So the notion of what is composite or what is fundamental depends on your parameters. You can tune one parameter to another, and it changes from being fundamental to composite, which means that there is no invariant notion to saying something is fundamental. It depends on which range you're at. It's duality frame dependent statement. It is not fundamental. Another example is in the context of string theory, we have a situation where you have two different strings. One of them is fundamental, what we call fundamental string, and the other one is a very fat, heavy string, which you can barely bend. But if you change the coupling constant in string theory, it turns out the one which was very light becomes stiff and hard to shake, and the one which was very stiff becomes so light, and it becomes the fundamental string on the other side. So the notion of what is fundamental or composite is not invariant. In the context of Feynman's path integral, we have learned in the context of general description of quantum mechanics, Feynman taught us that all you have to do is sum over all path histories. But to do that, you have to decide what are your fundamental entities. So doing this sum over these paths depends on which are the fundamental fields in your theory. So if you did this, you will get a well-defined answer in principle, a la Feynman taught us. However, we now know that there is no such notion of fundamental fields. So even the description of quantum mechanics in terms of integration over some fundamental fields does not have an invariant meaning. That's up also for well defined. Is the dimension of space-time well defined? Yes, look at it. 3 plus 1, we can see it. In other words, how could it not be well defined? It turns out that we can be fooled. For example, if you look at, there's a theory which is, let's say, 10-dimensional space-time. Here I'm drawing it like this, just one of its 9 spatial dimensions I'm drawing here. It turns out that if you change one of the parameters in the theory, you actually begin to see that actually this is not a line, it's actually like a cylinder. So one extra dimension opens up. So the 10-dimensional theory, if you increase that parameter, begins to look one more dimensional, like 11-dimensional. So the notion of the dimension actually changes here from 10 to 11. Now, you might have said, wait, this is silly. I would have just said it's 11-dimensional from the get-go, and I would just say that this is some limit of an 11-dimensional theory, right? That sounds like one possible answer. But actually, even that doesn't work. So let me try to explain. Suppose you go to this 11-dimensional theory and consider 2 of its dimensions identified periodically, or what we call in string theory language, put it on a torus, or like a donut-shaped object, and squeeze the donut-shaped object to 0 size. Well, then you're only left with 9 dimension, because 9 plus 2 is 11, and you're getting rid of this middle one. It becomes so small, you won't see it. So it's 9-dimensional. So you start with 11-dimensional theory, you squeeze this 2-dimensional space, you get a 9-dimensional theory, right? Wrong. 10-dimensional theory, it turns out. So you start with 11-dimensional theory, put it in 2 dimensions, squeeze it down. You thought you're going to get a 9-dimension, you end up 1 extra dimension out of nowhere. So the notion of dimension is not an invariant concept. You can gradually go from 11 back to 9 and back to 10 and so forth. All of these are perfectly connected, and it's not invariant to describe it. Is the topology of the space an invariant notion? Now, what is the topology? Like, if you have, for example, a surface, you can count the number of holes in it. For example, if you have a sphere, it has no holes. The donut-shaped object I was describing had 1 hole. A pretzel might have more holes, and so forth. So the number of holes is denoting the topology of that space. So if I just say I have a space which has 3 holes, does everybody agree that it has 3 holes or 4 holes or 5 holes? You would think so. Topology is a very basic concept in mathematics. Is that an invariant concept? Can we all agree on the topology? It turns out that this is not the case either. What appears to somebody having more holes, the other one will have less holes, and so forth. So these notions that are invariant, even rigorous mathematicians define these notions, do not survive the duality that we are talking about, that the notion of dualities changes from one side to the other. So for example, you can have a theory which you study it in the background of a surface which has, let's say, 3 holes, and that gets related to another one which has only 1 hole, to a different theory on a space which has 1 hole. Now you can ask the following. When we study quantum mechanics, when they teach us quantum mechanics, or when we teach our students quantum mechanics, we always tell them, you have already studied classical physics, right? Quantum mechanics is a slight extension of it with small corrections. Depends on which region of parameters you are. Those corrections could be bigger and bigger, but you can always start from the classical physics and view the quantum effects as like a power series correction to that classical description. So in particular, you have a power series. Is that notion well defined to say this is the classical part of the calculation and these are corrections? Can you separate the calculation to the quantum piece and the classical simple piece, which does not need quantum mechanics? Now, in the context of quantum theory, the parameter which controls this power series is what's called the Planck constant. So h bar, which is the famous constant that Planck introduced, If you set that to 0, we say these corrections vanish and you're just keeping the first term. The power series just truncates to the classical piece. Just like this. So you have some object you're trying to calculate. You have a classical piece, and then you have a power series and powers of h bar. And if h bar goes to 0, which means you're turning off quantum mechanics, you just get the classical piece. It turns out that even this turning off depends on which frame of duality you're describing it from. So for example, you can have the same quantity computed in 2 different frames. For one of them, it gives you an expansion like this. And for the other one, it gives you an expansion for this, where the h bar of the first theory is the parameter of the other one, and h prime of this theory is the parameter of the other one. Namely, these A1, A classical, A1, A2 depends on some parameters, A alpha. And these B's also depend on some parameters. It turns out that h bar of this first theory becomes a parameter of B. Let's say the first parameter or 0th parameter. And one of the parameters of this other theory becomes the h prime of the other one. So what is quantum from one perspective can be viewed as classical from the other perspective. The quantum mechanics, the quantum corrections are not universal. So even that is not well defined. So you can see now how difficult it is to come up with the final theory of this kind. It's revolutionizing all of physics upside down. Everything we thought was true is being under the question here, including things like what is classical, what's quantum, what's fundamental, what's composite, what's the dimension of the space-time. All these things are not invariant. And that is what that's what we are up against with one fundamental theory of this quantum gravity. It's that difficult to have to put all of these together. Another example, do black holes have microstates? Now, these black holes have, these huge objects, and I told you that they represent particles, energies of particles, which are these humongous things, and the number of particles corresponding to the black hole relates to the area of the black hole. There are a huge number of particles, roughly as many as exponential of the 1/4 of their area. That's huge. And how do we see this? Well, it turns out that we learned from a principle called holography that indeed this is true, that the area of the black hole is capturing what is the inside of it. In other words, the idea that like in a hologram, where you can see the 3D image of something in a 2D surface, somehow is happening here. That is, the ingredients inside the black hole are captured by what's happening at the area on the boundary of the black hole. So this principle is called holography, and this has been verified by numerous examples in string theory. And how do we see it in string theory? The way string theory answers this is the following. You ask, where are these states? Where are these ingredients, microscopic description of the black hole? And it turns out that these microscopic descriptions are hidden somewhere. You might ask where. On the other hand, string theory has extra dimensions. And you might ask, why does string theory have extra dimensions? What are they good for? And it turns out that one thing they're good for is exactly hiding these degrees of freedom there. So a black hole can be viewed as sitting somewhere in our space, but might be a string in reality wrapped around these tiny little spaces, which is coming from these higher dimensions that string theory needs for its consistency. So therefore, the resolution of what ingredients black holes may have may be related to these extra ingredients that are actually needed for the theory to make sense. Now, you could ask, I talked about electric force and magnetic forces, and I've also talked about gravity. Are they in any way related? Are they distinguished and so forth? Can one be related to another? It turns out that gravity can arise from gauge theories only. In other words, if you take the analog of electric fields, you can complicate or make it more complicated the electrical field. And it turns out if you do that, you effectively describe the gravity in one higher dimension. This principle, which is called also holography, precisely because you can describe the electrical fields and so forth living on the boundary of this space, is one of the main discoveries in the context of quantum gravity. So you're describing a space on the boundary, let's say a 4-dimensional space, on the boundary of a 5-dimensional space. The gravity lives inside here, And on the boundary of it lives these analog of the electrical fields that describe what's going on inside. So these electrical fields can kind of encode what's going on inside the geometry, inside this, which is gravitational. So this principle is related to the black hole principle of holography I told you, but it's a very general principle of quantum gravity theories. Holography, namely the boundary data describe what's going on inside. It's like a hologram. One extra dimension can be generated out of nowhere. So that's an example of that. So we have these kind of large dualities and geometries where you kind of think about this like this. You put some of these membranes or strings or something on some region. What happens is that it shrinks it, and then some dual description, some dual space opens up where you get the flux of these branes coming out. And this actually is a physical geometric transition from one shape to another. Underlies this holography. So there's a geometric transition going on. What about predictions for our universe? Well, it is a well-known fact that the ideas of low energy physics, what you want to describe the low energy physics called effective field theories, EFTs, fail to explain various fine-tunings that we have in modern physics. For example, in the standard model of particles and physics, we have an energy scale much smaller than the fundamental scale in physics, the Planck scale. Another scale, which is even more bizarre and much more fine-tuned looking, is the cosmological constant, lambda, what's called also sometimes the dark energy. It's extremely small, measured in fundamental units of physics. It's 10 to the minus 120 in fundamental units of physics. Very small, extreme small parameter, 0.0000 all the way up to 120 zeros, and then you get to a 1. Extreme, hugely, 1 over that is huge, and itself is extremely small. And I explained also that electroweak hierarchy scale, that the scale that we live in, that the electrons and the Higgs particle and the weak particle and so forth are much smaller than the fundamental scale of the theory, which is the Planck scale. So you might ask these kind of questions, and you could add to that list, why do we live in such a crazy time? What is crazy about, well, not politically I'm talking about. That too, but let's not talk about that now. That one I have nothing to offer as far as insights from string theory, unfortunately. Now, but we also live in a different, strange time where the dark energy, so let me explain what has happened. A few billion years ago, suddenly the universe recognized that the dark energy is the dominant energy in the universe and started exponentially expanding faster. So it was originally expanding like a power law, and then suddenly said, oh, there's dark energy is taking over, and suddenly goes fast, okay? And this happened relatively recently. By recent, I mean a few billion years is nothing compared to what it could have been, namely ad infinitum. It could have been 10 trillion, gazillion years, you just name it. Why did it happen just now? Why did it happen right as we were talking about it? Well, is it accidental that we live in this epoch? Or is it a good reason, for example? These sound like fine tunings. But as we have explained, one lesson we have learned is that the things that appear fine-tuning may not be fine-tunings after all. It could be that there are correlations between features of fundamental theory of physics, which look strange, but demanded by its consistency. And this is what we are discovering in string theory, that things which appear to our eye as being fine-tuned, because in the prior of what could be the possible universes, if we don't narrow it to that finite set that quantum gravity allows, we have the wrong prior. And on that wrong prior, it might look fine-tuned. But on the correct prior of that finite set, it may not be fine-tuned. So you begin to explain these fine-tunings if you pay attention to what this finite set is and why is there this finite set. So that's what one of the hopes are, that we're going to explain some concrete features of our universe, these fine-tunings, using these principles. In fact, they lead to a rather interesting perspective on dark energy. So the fact that the dark energy is small, I told you 10 to the minus 120 in fundamental units, turns out to be related. It demands that one of these extra dimensions of string theory should be large. It correlates the smallness of the dark energy to existence of one of these microscopic dimensions to be relatively large. By relatively large, I mean not infinitely large, I just mean micron scale. It suggests that our universe is like a sheet of a 3 + 1 dimension. Just think about our universe as a 3-dimensional sheet inside one extra 4th-dimensional spatial one times time. So we have one extra dimension, which is like a micron scale. And micron, as you recall, is the 1,000th of a millimeter. So it's small, but not atomic small. It's bigger than an atom. But that's the scale we are talking about would be expected of this extra dimension. And where do we get this scale from? It turns out that the dark energy predicts the scale. So the dark energy correlates with this extra scale. And the dark matter would, in this context, be related to gravity waves in this 5th dimension. So that would be a picture where the gravity waves unifies the dark matter and dark energy. So the dark energy demands the space to be big, and the gravity waves on it are the dark matter. So this kind of combines ideas from the dark energy and dark matter to get into one framework. So these are ideas which, from the viewpoint of effective field theories, looks bizarre, but from the viewpoint of string theory is extremely natural. And in fact, this means that if you put particles which are on our universe, and if you measure the gravitational force, which usually goes like 1/r², if you put a particle here and a particle far down there, their force goes like 1/r² for gravity. But if you bring them very close to each other, shorter distance than this 1 micron, it feels the extra dimension, and the force law goes from 1/r² to 1/r³. So if you bring particles together at a distance scale of 1 micron or less, you should expect to have a higher force between them. This is one of the predictions we are making, and this is actually already being tested by different groups, one of them being a group in Vienna, which is doing this experiment. And let me just see if I can, I just want to see that this kind of thing can actually be done, and people are actually checking it. The current bound is 30 microns. So up to 30 microns, we have seen by experiments that Newton's force law holds up, namely it's 1/r². We don't know what happens shorter, so we think something might happen at the micron scale, and we're extremely excited to check it. So let me conclude. String theory has led to new ideas that change our understanding of consistency requirements of quantum gravitational theories, and new principles have emerged that lead to new predictions. Can potentially lead to explanation of fine tunings in our universe using this relation between short and long distance physics.
Can you hear me? Yep. Okay. Thank you so much, Professor Waffer, for an amazing presentation. Are there questions from the audience? If you have a question, please wait until the microphone gets to you so that the people on the live stream can hear, and also everybody else in the room can hear as well. Go ahead.
What does string theory have to say about the fine structure constant?
If the question is what is its values, it doesn't say what its value should be. It certainly is consistent with potential examples in string theory, but it doesn't predict the value for this fine structure constant per se. So it doesn't say anything specific, no. So I would broaden your question perhaps to say, can we predict the masses and the charges and all that for our standard model using string theory? Now, I told you that the number of solutions in string theory is finite. So you might say, okay, just go and look, do you see that one among your list or not? The problem is that we don't have the full list. We think it's finite, but finite might be 10 to the 100, for example. And some of them may not have even been constructed. So I don't have this mechanism to go and check every solution. Otherwise, I would have been able to tell you, oh yeah, I know this one is the one we were talking about.
Up the back there.
Why one extra dimension?
Good questions. It's not obvious from what I said, but the way it works is that you can relate the smallness of the cosmological constant to the emergence of a tower of light particles. That's number one. And then you find that that tower of light particles, if it is a particular, if it's more than one dimension coming, if there was extra dimensions were more than one, you find that those light particles would have been already discovered in the experiments that we know it's not there. So we know experiment rules out the rest. So the combination of smallness of lambda and other experimental inputs gives only one option left, one dimension. So either that or no other one. So that's what we are forced. Not that we just didn't put it by hand. It was experiment plus theory kind of combined.
There's a question here in the gray body.
Hi, Professor. I have a question about the M theory. I don't really quite understand like how does it was R11 to and then becomes like T to the square and R to the 9.
Yes.
And in the opposite direction, it becomes like T to the square times R cross R to the 9, and it just becomes like R to the 10. Like how does this
happen?
Yeah, how does this happen?
Good question. So let me try to repeat the question. So that, as you recall, I was saying that suppose you start with 11 dimension, or let me actually simplify the discussion by bringing the dimensions down so everybody can visualize it. Suppose we had a 3-dimensional space and 2 of its dimensions on a square, and one of them is along a big line, okay? Now, suppose we shrink these 2 squares to a tiny, tiny square. What's the dimension left over? Just one, right? 1-dimensional line. And I said, no, it's 2-dimensional. That was the analog. I said 11 should have become 9 because you get rid of 2, but I said it's actually 10. So I want to explain why. Okay, so your question is, how come when you shrink these 2 dimensions, if you have a 3-dimensional space and shrinking 2 dimension, where did you get this extra dimension from? Where is it? I don't see it. That's the question. The way it happens is very interesting. What happens is in the M theory language, there are these membranes which are very massive. But these membranes can wrap this square that I was drawing here for you. And the energy of these membranes is its tension times the area of that square. If the area of the square shrinks to 0, those become very light because the area times the tension goes to 0. So they become very, very light objects, these membrane wrapped around this one. So then you get these light particles, and you say, what are these light particles correspond to? Now the dual description says, these light particles are like long wavelength excitations of a gravity in one extra dimension. That's how you get your extra dimension. So your extra dimension comes from these kind of connections, which is not obvious. So geometrically, you lose 1 dimension, but you gain it in terms of a new particle emerging.
Okay, could people with question put your hand right up so I can see them more easily? Okay, we'll go to the one in the middle there, and perhaps we could have a second microphone go to the person in the mustard jacket. Middle back. Blue shirt.
Hi. Where and how, in what direction do you foresee the future developments of the string theory? What topics for research are going to be covered in the next 10 years, and what results might we expect to see from those researches?
Good question. So I didn't tell you for example, what me and some of my colleagues are working on these days, which has to do with the dark energy. So one thing which has been discovered now, I don't know if you have heard the news or not, that the dark energy may be decreasing. I originally said cosmological constant. It turns out maybe it's not a constant and maybe it's changing. So I'm happy to say that we had predicted this like 6 years ago, that this may be happening using string theory. At the time, it didn't sound like a good thing to do because it was against the experimental observations. And our string theory colleagues kind of admonished us, why did you say this? But string theory ideas from swampland suggested that they may very well happen, and we predicted what kind of properties this potential might have, or how fast it might change. And the results that are coming out from experiments, from observations of 15 million galaxies by the DESI team, seems to actually give the same parameter range we were predicting. So these kind of things, when we follow up and continue in those directions, have a chance of connecting string theory ideas to the real world. I think that's one direction that we'll think, cosmology. Dark matter is the other thing. And it turns out that the dark matter and dark energy connection that I was telling you about plays a key role in potentially explaining the recent result that the DESI team is observing on these galaxies. So this is now connecting these abstract ideas, which sound like far removed from our universe, to actual observations and the parameters that they are actually getting from experiments. Another thing was the experiment I mentioned for the deviation from Newton's 1/r² law. Those are very concrete things, and try to understand features of this theory is another feature. And this is on the experimental physics connections with us. But purely theoretically, we would like to have a more unifying way of saying what I told you. What I told you sounded very fractured, admittedly. I wish I could have told you this is the principle and all of these follow from this. I didn't do that because I don't have that. So theoretically, one thing we should try to do is to try to understand overarching principle itself that is clearly giving you all of these as simple corollaries. That we don't have yet.
Okay, you over here.
Hi, and I want to follow up on that experimental efforts to verify the deviation from Newton's law. Can I ask more about the experimental platform? What exactly are they using to kind of try to detect this deviation? Is it very simple? They just take two masses and just bring it in 30
So
micrometers?
yes, what they are doing, this is not what I'm doing, but what they are, they have a situation where they have a disk, which looks like my fingers in the sense that they have massive, less massive, massive, less massive, like fingers, like my fingers on a disk, and they rotate. So it's a vertical disk rotating. And then on the other one, you have a torsional pendulum hanging on the other side. So when the heavy part comes near this side of the pendulum, it attracts. When the other heavy part comes, attracts the other side. So the pendulum starts wobbling with the frequency of this disk. So you tune the frequency of this disk to correspond to the natural resonance frequency of this pendulum and put them at a distance of around as much as small as you want, close to micron. Now, this is easier said than done because you can imagine if there are some few stray electrons on one side or the other, since the electric force is humongous compared to the gravity force, it will mess up the whole experiment. So you have to really screen it. You have to put some Faraday screen, which protects the electric field not to go from one side to the other, and this and that, which is difficult experimentally. But that's the kind of thing people are doing. So in idea, it's simple. In implementation, it's very difficult.
That's it. Thank you.
Okay, we could have perhaps two more questions. We've got one who's been very patiently waiting at the center back. We'll take that one first.
Thank you for the talk. So I would like to follow up on, you mentioned that the topology of the surface is also not invariant. So for which I guess is like, for example, the homology groups and cohomology groups are different depending on what are the parameters. And you say like the parameter space are kind of like path connected that you can go smoothly. So my question is like when the homology can change, then like a lot of physical properties depends on the homology. For example, quantum error corrections, right? So do you mean like from exists a smooth transition in the parameter space to make like one surface possible to do error correction and one does not?
There are two things one can say. First of all, when I say topology changes, I'm not talking about topology from the vantage viewpoint of a given theory. The topology from the vantage point of a given theory does not need to change. The point I'm making is that when you go to extreme ranges of parameters, there's a different vantage point, a different theory, which describes the same theory you're describing with the same homologies using a different homology numbers. So the homology numbers changes from a dual perspective to a totally different space. Like somebody says, no, the space you're seeing is not what you thought, it's something else. And then you would tell me, no, it's my space doesn't change. I will tell you, no, it has changed, but not to your eyes and not to my eyes. So we have we don't agree on the description, but we're actually both describing the same system. That's duality. So there's no contradiction in anybody's viewpoint. Now, having said that, the topology change is also possible in string theory, which is a different story. So I didn't talk about that. The topologies can change by themselves from a given vantage point, but I wasn't talking about that.
Thank you.
All right, is there worth one more question perhaps? I guess over here, and that will make that the last one.
Thank you so much. Like, just a quick question about the holographic duality. Like, I saw like you marked like ADS FT there. So as we all know, like our universe actually flat inside of like negative constant curvature. So like can you like talk something about like any progress on like flight FT, like flight 3, FT 2, something progress about that?
So I didn't hear the exact, can you say the last sentence, please?
Just like, can you tell us something about like the correspondence between flight to the SEPT or like QFT, like flight
yes.
3 to SEPT 2?
For our universe, you mean?
Yeah, for our real
Well, we don't
universe.
have that description. So the examples of the holography we best understand are the cases where you have this symmetry called supersymmetry. Those demand the dark energy be negative. Dark energy in our universe is positive. And we don't have supersymmetry. So we don't have such a description. People have tried to have such a description like in holography, but we don't have a holographic description for our universe. People have proposed something, but they're too tentative for me to describe.
All right, if that's it, let's thank our speaker again.
Thank you.
And just a reminder, there are refreshments outside the auditorium. Thank you, that was amazing.
Thank you.
For coming back to hear our second Welsh lecture today. So I'm Sergio de la Barrera, an assistant professor here in the Department of Physics, and it's my great pleasure and honor to introduce our second Welsh lecturer, Professor Pablo Herrero. So Pablo is currently the Cecil and Ida Green Professor of Physics at MIT, and he's actually one of the most influential and contemporary physicists in our field of condensed matter physics. His groundbreaking research has transformed our understanding of quantum materials, especially in recent years, particularly two-dimensional material systems, which is also my research specialty. He's best known for pioneering the field of twistronics, which we'll hear about today from Pablo. But even before that, he was extremely influential in the field of two-dimensional materials overall. His discovery in 2018 in particular of the fact that if you twist two layers of graphene, single atomic layers of carbon, on top of one another to a very particular angle, the so-called magic angle, changes graphene from a semi-metallic material into a superconductor, and in other circumstances, a correlated insulator. That's an insulator that is due to the interactions between electrons, completely changed the field. This sparked an explosion of interest in what's now called moire quantum matter, a new paradigm of quantum materials research, and it launched an entirely new research frontier, including the one that I'm exploring currently with my own group here at the University of Toronto. He's the recipient of numerous awards and honors. I promise I won't list them all, but I do want to mention a few key ones, including the Oliver E. Buckley Prize in Condensed Matter Physics, the Wolf Prize in Physics, the Medal of the Spanish Royal Physics Society, and the Max Planck Humboldt Research Award. Pablo's work continues to shape the direction of quantum materials research around the world, and his contributions are not only internationally recognized, but have also inspired a new generation of physicists like me, who are rethinking what's possible by engineering quantum systems to generate new phenomena. So without further ado, please join me in welcoming Professor Pablo Herrero.
Thank you very much, Sergio. It's really a great pleasure to be here at the University of Toronto. Thank you, Sergio, for the invitation. I happen to be a fellow of the Canadian Institute for Advanced Research, CIFAR. Some of you may know this institution. So I come to Canada very frequently, and I'm always extremely happy to come to Canada. So thank you very much for the invitation. It's a great honor. And it was interesting for me also to learn a little bit about, Harry Welsh and his very influential work in optical spectroscopy of molecules and Raman spectroscopy, many techniques that we actually use in my lab to do research on 2D materials. So it's a double honor. Thank you very much again. I want to tell you today about, the magic of, quantum materials and magic angle graphene, and you will understand immediately, about the twist and shout of quantum materials. But I want to start because I know that this is a, public lecture, and hopefully there's some people on YouTube. They told me, that might be watching this. I want to start from a very general, point of view. First, with what determines the properties of materials, okay? So, what would you think, let me ask the audience, there are many students here. What do you think determines the properties of material? How material behaves? Anyone? I had lunch with very, very talkative students. So some of you, what? Oh, no, that comes second. Something even simpler, That's kind of like the same as that. Geometry. Structures, same thing. Geometry, shape. Something else? Right, you guys are too advanced of an audience, Most people in these public lectures say, how about chemical composition, what the material is made of, okay? So, for example, if you take gold, gold is a good metal, okay? It shines. Actually, I don't know if everybody knows that you actually get to use gold in very advanced nanoelectronic applications, not just in jewelry. But, you think, okay, gold is a metal. For example, aluminum is also a good metal, but if you cool it down, it's a superconductor. So maybe, we need aluminum to have superconductor, but gold is not a superconductor, okay? Different chemical composition. Iron is a metal, and it's also a magnet, okay? All right, so now we have, certain elements, iron, nickel, cobalt are magnets, and silicon, for example, is not a good metal. It's a semiconductor. So maybe chemical composition is what determines the properties of materials, yeah? However, of course, you can go and dig a little bit deeper. How about carbon? Yeah? So we have on one hand, graphite is a material that is made, all of it is made of carbon atoms, and it happens to be an electrical conductor, right? But you also have diamond, which is also made just purely of carbon atoms, but it happens to be an electrical insulator, okay? So how come that despite these two materials being made of just exactly the same thing, just only carbon atoms, how come that they have such vastly different properties, okay? Electronic properties. Well, the reason is that, although they're made of pure carbon, the carbon atoms in graphite and diamond are arranged differently, which all of you had already suggested before, okay? They have different crystalline structures, different shape, different geometry of the arrangement of the carbon atoms. Huh? So now it seems that, you can see here, by the way, this is a zooming into what the structure of graphite looks like. So the carbon atoms in graphite, they are arranged in planar sheets. Yeah? Whereas the carbon atoms in diamond, they're in these tetrahedral, arrangements, okay? Three-dimensional arrangements rather than these two-dimensional arrangements. So both crystalline structure and chemical composition are important aspects that determine the properties of materials. Yeah? And it turns out that for a given material, nature, meaning the laws of thermodynamics, tell us pretty much about what is the favorable crystalline structure, and there's not too much you can do about it. I mean, there are a few cases like diamond and graphite where the same element can be in two different structures and the properties are different, but it's not like you can make diamond in 27 different structures. No, diamond is diamond and it's diamond structure. Graphite is graphite and it has this structure, and that thermodynamics tells us how this should be. That is, or that was, the case until 2D materials came onto the market, okay? So this is what I want to tell you about today. We're going to start with the twist with, very simple 2D materials. Again, I'm afraid this may be too simple for this highly trained audience, but we'll see. But, 2D materials, Legoland, twistronics. Then we're going to go a little bit deeper into what is graphene and what is magic angle graphene, what is magic angle graphene superlattices. And then I'll tell you a little bit, this was the twist and then the shout, what happened when we discovered correlated insulators and superconductivity, magic angle graphene. And a little bit, I told you a little bit about this emerging field of more quantum matter and some outlook. Huh? All right, so let's get started first with 2D materials, but 2D, what do I mean really by 2D? Okay, so let's start with 3D. Okay, imagine you have a deck of cards. This is a bulk 3D material, right? It has length, width, and height. Okay, it's clearly 3D materials. Now it's a deck of cards. So if you go and take only one card, that starts to look more like one-dimensional. It mostly has length and width and just a tiny bit of height, right? So it starts to look much more like a two-dimensional material. Now, let's imagine we have an apple. You all have tasted apples, hopefully. And I tell you, I'm going to slice this apple, a few slices. Do you think a slice of an apple, what does it taste like? Like what, a thin slice of apple, what does it taste like? Like apple, okay? Indeed. What I'm going to tell you about today is that type of materials that we're investigating, when you go from the 3D to the 2D, their properties change a lot. It is almost, not quite, but almost as if you took a slice of an apple and it tasted like an orange, right? You would be like, whoa, what's going on? So that is the type of things that we are, the electronic analog, is whoa. That's what I'm going to be showing you a little bit about. So now, of all the materials which are two-dimensional, the most famous is graphene, which is a two-dimensional version of the thing that is at the tip of your pencils, graphite. When you write with a pencil, I don't know if you've ever thought about it, but it's essentially the same thing as if you took a deck of cards and you spread it on a piece of paper, okay? So that's graphite spreading thinner pieces of graphite, the thinnest being one layer graphene. And this is what graphite looks like under a scanning electron microscope. You can see already that this looks a little bit like a deck of cards, right? Well, if you zoom in further, you see even thinner and thinner and thinner steps. Yeah? And if you zoom in and you zoom in and you zoom in, okay, you would see eventually something that would look like this or like this. This is a honeycomb arrangement of carbon atoms. It's one atom in thickness, and that is graphene. Yeah? Now, people, meaning physicists, okay, did not think that isolating an individual sheet of graphene was possible. There isn't even a theorem, in physics and mathematics/physics that says that this is impossible. Okay, as usual, you can disregard, mathematical theorems in real life because their assumptions don't always, apply to real life. Okay, so these two gentlemen, Andrei Geim and Kostya Novoselov, these two gentlemen, managed to isolate graphene. And they did it in a way which was crazy simple, almost too crazy, to believe that they would succeed, which was the following. They took graphite and they used Scotch tape. Yeah? And I know some of you are working in Sergio's lab and you can attest to the reality that you actually use Scotch tape, okay? Not something more sophisticated, but actually Scotch tape. So the way you can do this is the following. This is, by the way, my hand. So you take a piece, some crystals of graphite, okay? And you take a piece of Scotch tape and you put a piece of graphite on this Scotch tape, and then you fold it into two, and then you split this crystal, the single crystal, it gets split in two parts, okay? Because it's easy to exfoliate, okay? Because the 2D layers are only loosely bound to each other. It's a van der Waals material. Now you can then shift a little bit the piece of Scotch tape and do this again. So you split it into 4 pieces, then 8 pieces, and et cetera, et cetera, et cetera. And you basically do this until you get bored, more or less, okay? And this is the way it looks. And then you take a piece of silicon, a silicon substrate, and you put this Scotch tape, which is full of graphite pieces, and you press it down, and then you release it, you remove it slowly. When you do that, almost miraculously, okay, in that piece of Scotch tape, there are a few flakes of graphene sticking out, which are individual sheets, and they get stuck on the silicon substrate. So when you look with an optical microscope, you can do this, you just look by eye. You may find something like this. This is an actual picture through an optical microscope of, this is one layer of graphene, monolayer graphene, which is nearby something which is probably about 3 layers of graphene. Right? So this is one atom in thickness, and you're looking at it with your eye. And you made all of this with a little of graphite powder that you can get from any mine around the world, and Scotch tape. This is how these two Russians, Kostya and Andrei, did it. If you could use a transmission electron microscope, a powerful microscope that allows you to see the individual atoms, you see this. This is an actual image of a graphene sheet, where you can see the honeycomb of carbon atoms. Yeah? For this discovery, for the isolation and the initial examination of the electronic properties of graphene, Andrew Gam and Kostya Novoselov got the Nobel Prize in Physics in 2010. Okay? But now I'm going a little bit too fast in time. Let me tell you a little bit about how I got into this. So this is the way I looked in 2005. I was doing my PhD in the Netherlands, Delft University of Technology. Delft, beautiful small town. I encourage you all to go. So I finished my PhD in 2005, and that was about the time when graphene was discovered, shortly after. So I didn't know, okay, what should I investigate now for my postdoc, okay? And my PhD advisor popped up and said, have you heard about this amazing 2D material called graphene? Yeah? And I said, no, what is that? And he said, he told me a little bit about graphene. So then I went to Manchester and I visited Andrew Gam and Kostya Novoselov to learn how to do this Scotch taping thing. And they were extremely generous. They actually taught not just me, but many people around the world how to do this thing with graphene. So that made it possible for the graphene community to grow very fast, okay? They taught us how to do this thing, which is simple, but you would never do it yourself, unless you were as crazy as they were, okay? So indeed, I met them, for the first time then, and we've met many times since. And then I went to MIT. I stopped first at Columbia University for a postdoc, and then I went to MIT where I started to investigate the electronic properties of graphene. So what's so special about graphene? Many things, okay? It's the thinnest material that exists and that will ever exist. So it's only one atom in thickness. It can get thinner in terms of the material. Yeah? The electrons in graphene, conduct electricity the best out of any material. They also conduct heat. The thermal conduction is the best out of any material. It's the strongest material also in the world, okay? Normalized by its size. Yeah, it's an ultra strong material, yet at the same time it's flexible. It's kind of like a sheet, okay? It's very strong like this, but then it's very flexible. It's also transparent, okay? Mostly transparent. It only absorbs 2% of radiation, yeah? So it has many superlatives and many things which make graphene quite unique. From a fundamental physics point of view, electrons in graphene are also unlike any other material that had been studied until that time, okay, until that date. And it is because electrons in graphene behave as ultra-relativistic massless particles, a little bit similar to the way, electrons propagate through high-energy particle physics accelerators like CERN. Yeah? Now, in some sense, sometimes my colleagues and I joke that, you could look at CERN and think of a giant graphene sheet, with electrons going through it. In what sense do electrons behave, like ultra-relativistic particles? Okay? It's not that they go close to the speed of light. Electrons in graphene go at about the same speed as electrons in copper, but their velocity is independent of the energy that they have. In the same way that photons propagate at the speed of light, regardless of whether they are microwave photons, terahertz, visible, X-rays, gamma rays, they all propagate regardless of their energy at the speed of light. Electrons in graphene have the same property. Regardless of their energy, they go at the same speed, the Fermi velocity, which is constant. And the equations that describe the motion of electrons in graphene are those of the two-dimensional Dirac equation for massless particles. So same as for ultra-relativistic particles, but in 2 dimensions. Now, that may have sounded a little bit complicated, especially for the people in YouTube. So let me tell you, let me give you an example of how different electrons in graphene behave from other objects, okay? And let's start with classical physics. Yeah? So who is the most famous classical physicist? Newton, very good. So let's take Newton, Sir Isaac Newton here, and let's ask Newton to throw, something at a wall, not apples, that will be waste. Let's throw tennis balls at a wall. Let's put a wall in front of Newton, and let's ask him to throw tennis balls at the wall. This will be classical tennis balls, okay? So, of course, when you throw tennis balls at the wall, everybody knows what happens. The ball bounces back, okay? The ball cannot go through a brick wall. All of you have had this experience, right? Okay, good. Now, who is the most, or one of the most famous quantum mechanicists, quantum physicists, There are only 2 or 3 names probably that you will. Who? Heisenberg? Yeah, not that one, the other one. Who? Schrödinger, very good. So let's repeat this tennis ball experiment, but with quantum tennis balls, okay? So let's take Schrödinger. You cannot see it, but there is a cat there. It's even worse than throwing apples, is throwing cats at a... So let's give Schrödinger quantum tennis balls, and now let's throw the quantum tennis balls at the walls. What's gonna happen? You can tell me. Most of the time, what happens? It bounces back. But every now and then, okay, in a process which is famous called quantum tunneling, tennis ball will make it through the wall. That's a rare occasion, okay? It happens rarely, but it can happen. Yeah? This process is called quantum tunneling. For those on YouTube, if you think this is exotic, all your electronics works based on this, okay? So you use it every day, your cell phones, the transistors in all your computers, everything. You need quantum tunneling, otherwise it will not work. But that's something that happens and that has been well known for, for many, for over, for 100 years or so now. Now, let's do this experiment with ultra-relativistic tennis balls. Who's the most famous relativistic physicist? Einstein. So let's bring Einstein here, and let's give him, let's put a wall, and let's give him ultra-relativistic tennis balls. Who knows what's going to happen now? And the experts, Sergio cannot say it. Well, what happens when you throw ultra-relativistic tennis balls at a wall is that the ball always makes it through 100% of the times. That phenomenon is something called Klein tunneling, okay? Klein tunneling, and it's something that was hypothesized, in the 1920s by Oscar Klein, never to be experimentally realized with ultra-relativistic massless particles, because it's kind of an awkward experiment. But about 10 years ago, 15 now, this was demonstrated with electrons in graphene, direct demonstration of Klein tunneling, because electrons in graphene behave like ultra-relativistic massless particles. And in fact, that effect is mostly, not entirely, but mostly responsible for the very high electrical conductivity of electrons in graphene. Because in most materials, take copper, electrons, they propagate through it and they're constantly bouncing off walls, obstacles. And they bounce back and then they go a little bit further in advance and they bounce back and then, but the electrons in graphene, they go through obstacles because of this process, okay? And that's why they conduct electricity so well, okay? Now, I'm oversimplifying things. The experts don't, this is roughly true to zeroth order, okay? Now, we have more 2D materials. Graphene was the first one that was discovered, but we have plenty of other 2D materials that we have discovered since, okay? This includes hexagonal boron nitride. This is also a 1-atom thick material where you have alternating boron and nitrogen atoms in the honeycomb structure, okay? Because now you break the symmetry. All of these are no longer carbon, but they differ, boron, nitrogen alternate. This actually turns out to be an insulator. It's the thinnest insulator in the world, 1-atom thick insulator, okay? Very useful for many things. I will tell you a bit more about boron nitride tomorrow in the colloquium. You also have other materials which are not 1 atom in thickness, but they're 1 single unit cell in thickness, yeah? So for example, tungsten diselenide. This is a member of a large family of materials. And tungsten diselenide from the top, it looks also like a honeycomb, tungsten and selenium atoms, but from the side, it actually has 3 layers. The unit cell is 3 layers, 3 atomic layers in size. This turns out to be Not an insulator, not a metal, but a semiconductor where the electronic properties change dramatically with the number of layers. For example, it emits light of different colors depending on what's the number of layers. 1, 2, 3, 4, emit different colors of light. Yeah? Well, not so recently, actually, 10 years ago, in my own group, we made, the world's thinnest LED, less than a nanometer in thickness, okay, out of tungsten diselenide, okay, this semiconductor. So this is something that a lot of people, graphene is a little bit too exotic with this ultra-relativistic behavior, but this behaves like a regular semiconductor. So it's the ultimate semiconductor that people in industry think will allow Moore's law to continue for, a few extra years, okay? Because the ultimate thinness for a semiconductor. Now, you can have 2D materials, but you can say, well, why don't we go back to 3D by stacking these 2D materials? And in fact, the nice thing is that we can stack these 2D materials one on top of each other with any arrangement that we want, changing, materials, do graphene, boron nitride, tungsten diselenide. Or we can say, oh, no, I don't like that one. I like this other one, where I put these 3 layers first, and then I put this other one. And you can do, as you can imagine, infinite number of combinations of these things, okay? This reminds me a lot, I tried to explain this once to a chef that came to see me at the lab, and he was not getting it until I told him that this was exactly the same thing as doing this, and then he got it, this is, okay. For cooks, this is simple to do for us too. This possibility of stacking, 2D materials on top of each other has led to analogies with what people call 2D materials Legoland. And you have articles by friends and colleagues where they put, they make this analogy. This is like putting Lego pieces on top of each other. This is, a very good analogy, but it's not the most complete analogy or not the most powerful thing you can do with 2D materials. Yeah? So I have small kids. Those of you that have small kids, or probably those that don't, have still played with Lego. And sometimes, my son comes and tells me, Daddy, I cannot stack this piece of Lego on top of the other. And I tell them, look, this is because you have to align them to 0 degrees rotation. Only now you can stack them. And I go, oh, yes, or 90 degrees, right? So while these analogies with Lego are very powerful, 2D materials allows you to do something which was completely unprecedented in the history of material science, which is the following. You can take a 2D material, for example, graphene, and you can put another layer on top, but you can do that with any angle of rotation between the 2 crystalline structures that you want. That is something that we couldn't do in the history of material science and physics until 2D materials came. We can place one on top of another with any angle the rotation of we want. For example, 30 degrees, 27, 1.1 degree, why not? I'll show you later, okay? And it turns out that the electronic, all the properties, mechanical, etc., optical, but especially the electronic properties of the composite structure at a given twist angle can vary dramatically, change completely with respect to the constituent layers that we put together, okay? This is the apple-orange effect. So when you do this thing, you form a super periodic pattern. I will show you a bit later more. And that thing is called a Moiré pattern. When you put 2 structures, which are periodic, and you rotate one with respect to the other, you form a super periodic structure. Yeah? So let me tell you now a little bit about graphene and magic angle graphene. Yeah? So graphene, if you put graphene on top of graphene, okay, and you rotate it, you form this Moiré pattern where the Moiré wavelengths, the distance between the soccer balls that you see here on the screen, depends on that twist angle, that angle of rotation. Okay? Can go all the way to infinity because these structures are identical, graphene on top of graphene. If you have 2 slightly different structures, you get a Moiré pattern even without rotation at 0 degrees, okay? Because it's slightly different. But for graphene and graphene, this is what it looks like. Now, what is the difference between graphene and magic angle twisted bilayer graphene? Yeah. So tomorrow in the colloquium, I'll go a little bit deeper into it. But for now, let me just tell you this. This is the way the electrons in graphene, the kinetic energy of electrons versus momentum of electrons in graphene looks like. Looks like this. linear. Okay? Remember, I told you this is like massless particles. You know, photons have also a cone. Their energy dispersion is a cone. Okay, this is momentum. The same thing in graphene. The slope of this cone gives you the velocity. Okay, and it's constant at any energy in the cone. Okay? So this very steep slope means the electrons in graphene are very fast. Okay. What happens, and this, you know, this ultra-relativistic massless behavior, sound like that's because of this, okay, because of this cone. It's called a Dirac cone, actually. Now, if you get graphene on top of graphene, and you rotate it, or you stack it on top of each other at precisely 1.1 degrees, okay? 1.3 doesn't work, 1.1, okay? Plus minus 0.1, more or less. Then you get the following. The kinetic energy of the electrons versus momentum becomes this blue, much flatter relationship, okay? The small slope here, remember the slope is giving you the velocity of the electrons. The small slope here means the electrons are very slow. Now, this is fundamentally very different, okay? Because when electrons, you know, these are called, by the way, the flat bands. For fast electrons, the electrons have most of their energy in the kinetic energy. So the interaction energy between the electrons, the Coulomb repulsion, because electrons are like charged particles, is sort of often insignificant or can be disregarded compared to that very big kinetic energy. On the other hand, for slow electrons, right, now the kinetic energy is very small, so the Coulomb energy of repulsion acquires a disproportionate importance in the behavior of the system. I sometimes make this analogy, which is not, you know, it's not perfect, but for, again, for people on YouTube might help understand this. This is something similar to people walking in New York or walking in a small town, you know. People in New York walk very fast, you know, and they barely interact with each other, you know. They don't have time to talk to each other, you know. People in a small town, they walk much more slowly, and at the, you know, they get time to speak, and a lot of things happen. There's a lot of interactions, and there's a lot of time for something to happen, including magic, okay? So that's the difference between, you know, graphene and twisted Vallejo graphene. Now, how does this matter, you know, the question of whether electrons do not interact with each other, and we can think of them as single particles, or whether they interact very strongly with each other? Okay? It matters a lot. Okay? When we get a single electron spin, for example, the behavior of a single electron is mostly understood. It's relatively simple. It's mostly understood in quantum mechanics. Okay? However, when you get many electrons which interact all with each other, okay, that behavior of many interacting particles is difficult. And by that, I mean, it's not understood. Okay? However, in the universe, most of the fascinating states of matter that we have are of this type, of the type that we do not understand because they're too complicated, because they involve interactions between many particles. Okay? And this includes all kinds of behaviors, not just in condensed matter physics. It includes behavior, the behavior of the quark gluon plasma, which is a state of matter that appears, you know, a few nanoseconds, microseconds after the Big Bang. It is what happens also in the different phases of nuclear matter in neutron stars, which are objects that occur after a supernovae explosion. It also happens in correlated quantum materials, such as high-temperature superconductors. Yeah? So this type of behavior cannot be described. We don't know how to describe it theoretically very well, how to calculate it in particular very well. And as a result, this is something which is, you know, very difficult, and the community, you know, in all areas, you know, is struggling to fully understand. The way we have been investigating in condensed matter physics and related fields, strongly correlated matter that interacts very strongly. Traditionally, we've been looking at quantum materials with typical length scales of, you know, 0.1 nanometers, 1 angstrom. That's the distance between atoms in solids. Okay. When you use this platform, you have relatively little control over the properties of the system. You know, if you want to study a different phase of matter, typically you have to grow a different crystal with different chemical composition, etc. About 25 years ago, the community developed this other alternative platform, ultra cold atoms in optical lattices. Here you create a periodic potential by shining lasers at each other, which interfere. And then you can load that periodic potential with atoms, okay? And you can change the interaction between the atoms, yeah? And therefore you can try to study what happens when you have, many particles where you can change the interaction between them and so on and so forth. Here, unlike this case, here you have exquisite control over all the parameters of the system. It's amazing the degree of control that the cold atoms community has in the systems. However, the issue here is that they haven't been able to realize yet many phases of quantum matter, because typically these systems are still in the very high temperature limit compared to the physics that you would like to explore. And what has happened in the past 6-7 years is that a new platform has emerged, this Moiré quantum matter platform. Here the length scales now are not atomic distances or the wavelength of light, is this Moiré wavelength scale, yeah? Which is about 10 nanometers. And with this platform, we have not as much control as the cold atoms community has, but much more than this one, the traditional condensed matter physics. The difference is that here we have been able to realize pretty much all of the phases of quantum matter that we know, and discover even a few ones that weren't known before. Okay? So with magic angle twisted Vallejo graphene in particular, this gets now a little bit more technical, but these Dirac cones that are tell you the kinetic energy of the electrons versus momentum. Yeah? If you have a Dirac cone in layer 1 of graphene and Dirac cone in layer 2 of graphene, these, because we have a twist angle between the structures, now they're separated in momentum space. This would be the situation that would be realized if the electrons in one graphene sheet did not know that the other graphene sheet exists. However, because these two graphene sheets are right on top of each other, the electrons are very much aware that the other graphene sheet is there. In particular, they can tunnel between the two graphene sheets. Yeah? That interlayer tunneling gives rise to a gap opening there at the intersection point of those electronic structures. This gap opening, this is like bonding anti-bonding states in a hydrogen molecule. This is bonding anti-bonding bands in a giant bilayer graphene molecule. Yeah? That opening here, this interlayer tunneling, is small at very large twist angles compared to the energy of that point. But if you now decrease the twist angle, these two Dirac cones get closer and closer to each other. That band gap opening, which is pushing down one of the bands, pushes down the band towards lower and lower and lower energy, until at a certain angle you reach, that thing goes to zero, that band goes to zero. You reach something which is known as a flat band condition. And this flat band condition is reached at the magic angle, which for graphene on top of graphene happens to be 1.1 degrees, okay? That was something that was theoretically predicted by several groups, like McDonald Group and by a group in Chile. There was also some experimental work by the group of Eva and Ray on the single particle physics. This is all single particle physics up until now, okay? There was some prediction and some experimental work on this. Now, this is a cartoon. This is an actual calculation of the electronic structure of magic angle twisted Vallejo graphene. These are the flat bands. This is flat in momentum space. So if we want to go back to that Moiré pattern and see where do the electrons like to be, if I put them on this magic angle twisted Vallejo graphene, to go between momentum space and real space, you have to do a Fourier transform, okay? And when you do a Fourier transform of a very flat object, you get a highly peaked object. So if you look at where do the electrons like to sit when they are on those flat bands here, turns out they like to sit in certain regions in your Moiré pattern where the atoms between the two graphene sheets are locally aligned. We call it AA stacking, meaning all of the carbon atoms seem to be locally on top of each other. Now, because of the small twist angle, if you move a few nanometers, the lattice of atoms, get misaligned, I mean, they shift. And in those regions, the electrons do not like to be. So magic angle twisted Vallejo graphene schematically looks like this. It looks like, these AA regions where the electrons like to be, and then we have these AB and BA regions where the electrons do not like to be. In a slightly more realistic schematic, this is what magic angle twisted Vallejo graphene line looks like. You have these A8 regions shaded in yellow. These are spaced by about 13 nanometers, yeah? And the electrons like to be there. This is going to be a little bit of an analog of a, ultra cold atoms where we have our lattice where we'll put the electrons in certain positions. So it has that component of, quantum simulator with ultra cold atoms, okay? It's not exactly a good analog. I'll tell you tomorrow a bit more about that. Now, so you make this thing, okay? What happens then? Let me first tell you how you actually make these devices, okay? So you take, this is very simple, more or less, my students might disagree, but it's quite simple. You take a glass slide with a polymer stack, okay? You have a sticky polymer. Now you bring a substrate which has hexagonal boron nitride, not one layer, but thick, 10 nanometers thick, okay, on it. And you pick it up with a sticky polymer, okay? There you go. Now you bring another substrate with a sheet of graphene, which we exfoliated with Scotch tape. Okay, everybody can do that. And we position this hexagonal boron nitride more or less halfway on top of this graphene sheet. Okay? So then I come with it down and I tear half of the graphene. So now from the top view, we have the substrate with half of the graphene, and then we have the glass slide with the polymer, with the HBN, and the other half of the graphene on top. These are at different heights, but the locations of their atoms are correlated because they come from the same crystal. Okay? So what we can do now is we can rotate the substrate by any angle that we want, 1.1 degrees, why not? And we can shift it and then stack it, one graphene sheet on top of the other. And then we pick up this graphene sheet. And amazingly, this produces that regular moire pattern, that the electrons now are going to live in. Yeah. After this, we do some nanofabrication. Okay. The devices end up looking like this. You have your twisted bilayer graphene here. It has boron nitride on the bottom and on the top. That's just to keep it, pristine and nice. The boron nitride plays no role other than being a high-quality dielectric for the purposes of today's talk. And you can contact it with source and drain electrodes so that you can apply a voltage and a current circulates through the device. Very importantly, we have also a nearby metallic electrode, a gate electrode, such that this gate electrode and the twisted bilayer graphene form a parallel plate capacitor. So if we apply a voltage, we can change the charge density in the plates of the capacitor, in particular in the twisted bilayer graphene. Okay? This is a field effect transistor geometry for those of you that know a bit more about engineering. So I will tell you a bit more tomorrow about how we did this, but basically what my group did in 2018 is that when we measured, devices which had twist angles very close to that 1.1 degrees magic angle, this is the way the conductance looks like. All you need to know, okay, tomorrow I'll explain a bit more, but all you need to know for today is that the conductance sometimes is 0. Okay, so we have a material which is the best conductor in the world. We put it on top of itself, and sometimes it doesn't conduct at all. And other times it becomes a superconductor. Okay, the single sheet was the best conductor in the world, but not a superconductor. So now I stuck it on top of itself, and it can either be the worst conductor in the world, an insulator, or a superconductor. Okay, and that I can tune by angle, and I can tune by varying the density of electrons in the system. So that's something, that was very exciting. In particular, this phase diagram of resistivity versus charge density and temperature, let me show it here. The moment my students showed me this phase diagram, it reminded me of the hundreds of times that I had seen the following phase diagram. This is the phase diagram of the high temperature cuprate superconductors, the most famous correlated quantum material class family. Now, let me put the axes here exactly, so that they indicate, they are parallel to each other. In the high temperature cuprate superconductors, I will mention this a bit more tomorrow, but you have a correlated insulator state called a multi-insulator when there is no dopants, which means 1 electron per unit cell. If you put a few extra electrons, or if you remove a few electrons, you get superconductivity. In magic angle twisted bilayer graphene, you have a correlated insulator when you put 2 electrons or 2 holes per Moiré unit cell. If you dope with holes or you dope with electrons, you get superconductivity, okay? There are many analogies between this phase diagram. There are also many differences. One of the most important ones is that this is something, this is a theoretical phase diagram. To populate it with experimental data points, you have to grow hundreds of crystals with different chemical compositions and with different materials. This is all done in a single material, just dialing a voltage knob, and it takes me a few seconds rather than a few years to explore this. Yeah? So that's something which is an important difference. All right, so we posted this, in the archive in March 2018, and then what I call the theory tsunami came, which is that, this is just a list of the papers that appear within the first, 2 or 3 weeks after we posted, our results. This list now has about 10,000 papers, okay? So everybody wanted to know, what is the origin of these correlated insulator states and what is, the origin of the superconducting, or the parameter, what is the superconducting or the parameter. All kinds of proposals were put forth with, proposals including all letters of the alphabet. There's this S superconductor, P superconductor, D, F, G, S plus P, P plus IP, D plus ID, all possible combinations, of the letters of the alphabet were thrown. We do not know yet what is, the actual superconducting or the parameter, but we have narrowed down substantially now experimentally. It can no longer be all of those options. Okay, now there are much fewer options that are possible. I always joke, that in this field of strongly correlated physics, things are very different from the graphene, where I used to work, before 2018, vanilla graphene, In the field of just regular, graphene, the angular cone of disagreement between theorists is about 20 degrees, I would say, more or less, In this field of strongly correlated physics is 360 degrees, In fact, it's 4 pi, it's in all directions, of space. So to me, sociologically, it was quite interesting to see how, people could have completely different ideas about what, this behavior was about, Now, rather than tell you about, by the way, yes, so this, to my surprise, this not only led to many papers in the archive, but also many papers in journals with fancy figures, with 1.1 degrees, things that look like your speed meter in your car, It's, was quite attractive for the popular press too, apparently. Now, let me just tell you very briefly, tomorrow I will expand on this, on what has happened since the discovery, okay? Especially, we're focusing on the experimental developments. So the first thing that happened is that we have reproduced our own results in my group. Believe it or not, it doesn't always happen that you reproduce yourselves. It's very good, okay? When you can do that, that's the first thing you want to do. Now, much better than you reproducing yourself is when other people reproduce your results, okay? Only then it becomes real science. Unfortunately for us, many, many, many groups by now have reproduced our results and extended them to many other interesting systems, okay? So that's great. Plenty of other phenomenology characteristic of quantum materials has been observed, okay? For example, strange metal behavior, nematicity, Fermi surface constructions, cascades of phase transitions, pseudo-gap physics, all kinds of things. I'll mention a few of them, tomorrow. We have discovered many other correlated systems based on this Moiré quantum matter, okay? ABC tri-layer graphene aligned to HBN, magic angle twisted bilayer graphene. This is 2 layers with 0 degree angle, 2 layers with 0 degree angles, twisted among themselves. We call it twisted by, Moiré transition method dichalcogenized. By now, there's several dozen systems, of correlated systems based on this Moiré structure. People have discovered, ferromagnetism, anomalous hole, and integer and fractional quantum anomalous hole physics in this system, which was something very important because it brought the role of topology front and center into this research field. In fact, one of the things which I'm happiest about is that in this field, of Moiré quantum matter, it has meant the merging of several modern condensed matter communities that didn't interact that closely before. The people that did 2D van der Waals materials, graphene, and so on, like myself, and then the people that studied, strongly correlated materials, cuprates, pnictides, heavy fermions, and so on, and the people that studied topological condensed matter physics, quantum and fractional quantum Hall effect, topological insulators, bi-semi-metals. All of these 3 communities come together in this Moiré quantum matter because it exhibits all of these behaviors and very intertwined between them. Now, these systems are two-dimensional. So you can come with a microscope and look at them, okay? So all scanning probe, local probe techniques have been applied to these systems. I will show some examples tomorrow, okay? So people have done scanning tunneling microscopy, scanning nanosquid, scanning single electron transistor, scanning near field optical microscopy, scanning transmission electron microscopy, and even new techniques have been invented to look at the systems, such as something called the quantum twisting microscope that I'll mention briefly tomorrow. Now, you may think that, oh, this is great. You can put two pieces together, but why stop at two? Actually, you can put 3 and 4 and 5 with different angles and so on. So there, what is known as next generation Moiré quantum matter, Moiré magic 3.0, 4.0, 5.0. Turns out all of these things also have magic angles that they behave differently and so on and so forth. Okay, so I will mention again something about that tomorrow. In the last 2 minutes, I want to tell you a little bit about how this Moiré quantum matter is impacting even beyond condensed matter physics, okay? So we have, these 3 platforms to study now, strongly correlated and topological physics. And the magic of Moiré quantum matter is that within a few years, we have realized pretty much all of the phases of quantum matter that exist, and quite a few new ones that didn't exist, and often the ones that exist with very unconventional twists, okay? This is all done, by the way, with single element, carbon, or maybe, using a couple other elements, okay? So it reminds you the importance of, composition. A chemical element that you have is not that important as you might have thought at the beginning, okay? Other things are much more important, yeah? Now, because, these things that I have told you about was mostly about twist electronics, yeah? But it turns out that other communities are also copying these tricks from the condensed matter. So there is this thing called now Moiré and twisted cold atom lattices, because the trick that you can do with electrons, you can do with cold atoms. So there are these papers of cold atoms in twisted bilayer optical potentials. This is theory, the first theory paper by Ignacio Cirac about this thing. He's one of the leaders of the entire cold atoms field. And in China, they realized already optical, lattices, which are twisted, where they start to realize some of these things. The single particle effect responsible for slowing down the speed of electrons can be also used to slow down the speed of phonons, for example. So there is this field of Moiré and twisted phononics, okay, where you can make flat bands in magical vibrating plates. You can do this for macroscopic plates, like chunks of stuff, and for at the level of phonons, for microscopic, vibrations of lattices too. Yeah? You can do the same thing for photons. So there is this field of Moiré and twisted photonics, because you can slow down the speed of light tremendously by twisting photonic lattices. This is, in fact, other than the electronics one, this is the fastest growing field, with entire programs in the US dedicated to this, because you can slow down tremendously photons, and you can realize all kinds of optical nonlinearities and all kinds of interesting physics with that. Yeah? But why stop there? It turns out that these local regions in the Moiré pattern have very different density of states, which means also they can have very different chemical reactivity and catalytic properties. So there is this field now of Moiré and twisted electrochemistry and catalysis, where people are investigating with atomic force microscope, doing local chemical reactions in different places in your Moiré pattern, and they can see that they behave differently in the chemistry. And also there are these predictions for interesting catalytic properties of these Moiré twisted lattices. And last but not least, our high energy friends also thought that they might look into this. So there is this field of Moiré gravity and cosmology now, where apparently, when you twist, your thin sheets, you can actually find some interesting analogs of things that happen in gravity, and in cosmology, and all kinds of things which people are starting to look at. So with that, I want to end with what I think is, perhaps the most important slide. This is work that, it's not done by me, but it's done by a large group of people, okay? My students and my collaborators. Sergio, he didn't say it, but he was a postdoc in my group, and he contributed to some of the, work that we have been doing all these years. Thank also funding and support. As I mentioned earlier, I'm a fellow of the Quantum Materials Program of the Canadian Institute for Advanced Research. So I'm extremely appreciative of what Canada is doing for the condensed matter community and in general for science. And I'm hoping that we can maintain those strong links between Canada, the US, and the rest of the world forever. So thank you very much. I'm happy to take questions.
Thank you, Pablo.
And because I'm a little bit forgetful, I had brought a toy to demonstrate these Moray patterns. It's a Moray simulator. While the questions are running, I'll pass it around so that you can play with it and get mesmerized with these little toys, you know.
Okay, thank
You
you,
can,
Pablo.
you have to use your 2 hands to rotate this thing. Yeah.
Okay, so now we can take questions from the audience. Please raise your hand and then we'll bring the microphone to you. Okay, there's one, we'll do this one in the middle and then we'll come to the one on the left side.
Hello, you talked about how this research merged together some different research communities, and I was wondering if you could talk about what the difference is between strongly correlated materials, topological condensed matter physics, and 2D materials.
Very good.
Thank you.
Very good. So, you know, the community that studied 2D materials, graphene and transition metal like chalcogenides, plenty of they have very interesting properties because they're unusual. For example, this conical dispersion of the electrons in graphene, that's very unusual. There's no other solid that had that at the time. Now there are a few others that do. But it's a single particle effect, okay? Single particle physics effect. It doesn't have that interactions thing. It also doesn't have strong topological physics in it. Yeah? So there was a community that didn't talk so much to the high temperature cuprates or the iron pnictides or the heavy fermions community where they study electrons which interact very strongly with each other. Okay? Now that community, those electrons interact very strongly with each other and it gives rise to all kinds of properties. But for the most part or largely, topology doesn't play an essential role in those systems. There is another community that studies the quantum on the integer and the fractional quantum Hall effect, etc., where topology is the key thing. You know, that's why the quantization of the conductance in the plateaus and the quantum Hall effect is precise and perfect because, you know, it's an integer times or a fraction times fundamental constants, okay? And that's why it's so precisely quantized, yeah? So these 3 groups of people, you know, they talk a little bit, but it's not like they were talking all the time. In this field, you have 2D materials that interact very strongly and where the topological properties are essential, you know, to understand what's going on. So all these 3 communities, particularly the theorists, but also to some extent the experimentalists, are talking to each other very frequently and they're learning from each other. And that's how this is happening.
Thank you so much. Like, so I saw like you shows a video like thing on your slide, like just something like this one here.
Yeah.
So I'm wondering, will the physical behavior change if like we slightly, I mean, there's a kind of displacement between like unit cell center, like between the two layers of graphene, like will this change the physical properties or not?
Do you mean if instead of having pure rotation, you have translation?
Yeah. With both rotation and translation. Yeah,
Very
thanks.
Excellent question. So when you have a small angle between the 2 sheets, like, you know, 1 degree, okay? This quasi-periodic pattern that forms is more or less the same regardless of the translation between the 2 sheets. You have the same quasi-periodic pattern, okay? The same Moray pattern. And in that sense, it doesn't matter too much. You know, it would be very good or bad, depending how you think about it, if it mattered a lot, because then it would be very hard to always precisely have the sheets aligned with the same translation, with the same shift, okay? So it doesn't matter too much. There are other properties, and in particular, for 0 degrees angle, where that shift can play an important role, okay? So there are aspects of it where the shift, the translation shift matters. Also for larger number of layers than 2, it can matter, okay, the shift. Yeah? But for many of the key properties and the most essential properties, it's not very relevant. So it's a parameter that we cannot control very well. We can control it to some extent, but not very well. But thankfully, it's not essential for many of the properties that we're seeing.
Question in the back.
Hi, thanks for the great talk. I'm kind of wondering, on one slide you showed, as you keep twisting the 2 layers, how the original Dirac cones get deformed into the flat band. But the Dirac cones come from the original Brillouin zone of the single layer graphene. But when you go to this Moray lattice, because it's so much, the periodicity is like in the superlattice form, I would think that the Brillouin zone gets contracted to a very small region. So I'm wondering, how does the original periodicity survive in this twisted, larger structure?
Very good, excellent question. I will talk a bit more about that tomorrow, okay? But it is true. So we have, Angstrom scale original honeycomb lattice of graphene, yeah? That leads to a Brillouin zone, to a reciprocal space, which is very large because the distance is very small. When we do this twisting, and in particular at the magic angle, 1.1 degrees, the unit cell includes about 10,000 atoms, okay? This 10 nanometers, 10 nanometers is like 100 angstroms, it's 100 by 100, 10,000 atoms, okay? So the Brillouin zone is correspondingly 10,000 times smaller, okay? The Moiré Brillouin zone is called, okay? If you had an angle which was commensurate, okay, that's easier to, in general, it's not, and it doesn't matter too much, but to think about it, it's a bit easier. If the angle was commensurate between the two, meaning at whatever angle you twisted, it was a periodic, truly periodic pattern, that means that the Brillouin zone, the Moiré Brillouin zone would be one, let's take the case 10,000. 10,000 of them would occupy the Brillouin zone of the big, original graphene lattice, okay? So that original periodicity, is not that relevant. Your bands get folded and you have 10,000 bands, Moiré bands, folded on top of each other. The one that matters is the flat band near the Fermi energy, okay? The others can also be explored, and it's interesting and people are looking at them, but the most relevant one is the flat band, in the small Moiré Brillouin zone near the Fermi energy.
Yes.
Hi, so my question is, have you done any studies or thinking about what might happen if your angle was sort of dynamic over a sample? Like say you start at 1.0 and went 1.1, 1.2, like would anything interesting happen from that?
Excellent question. So I showed you, you can make a video of what would be the electronic structure precisely as a function of angle. And you can see actually how those steep Dirac cones become a little bit flatter, and they collapse at 1.1 degrees, and then they change again, and so on. When we make devices in my lab, we just make, we can choose any angle that we want, but if the angle is fixed when we make the device. A new technique has been invented called quantum twisting microscope. I'll mention briefly about that tomorrow, where you can actually continuously change and look at the electronic properties as you continuously change the angle. So that's something that's amazing. Everybody's super excited about that technique. I'm trying to set up one in my lab. Sergio, I just learned today that he's also setting one up in his lab, because it allows you to look at the properties as a function of that twist angle continuously, as a continuous parameter. It's something, again, that could never be done before, and now one can do it. So this technique was discovered, was invented in 2023, okay? And one group in Israel right now is doing that, but that group is also teaching a few of us how to do it, and it's very interesting. So some results are starting to appear, okay, but it's a very new thing.
Please.
Hi, thank you so much for your very informative talk. I just had a question. I'm not exactly sure if there's any connection, but for the two layers, are there any electronic properties that, for example, one layer, if you send a current in a specific direction, that would affect the twisting. So you could actually measure the twisting depending on the topology. Let's say you send a light or a current or something like that.
So I'm not sure exactly what you mean by, when we send the current, it gets distributed between the two layers, okay? Now, you can imagine a situation where you had one of the graphene sheets sticking out more than the other, and correspondingly the other one too, so something like this, so that you could send current through one layer, which would then be distributed between both of them, and then come out only as one of them, for example, through one of them, okay? You can do those things. The electronic properties of the material change a lot by the angle. So when you measure it, okay, when you send a current through it, we know what the angle is, because the way current is conducted through these two sheets depends very sensitively on the angle, okay? I'll mention a bit more about that tomorrow. So once we measure the device, we know what the angle is, yeah? And then once you have that, we can do all kinds of things. In terms of, for example, optics, these structures are chiral. Okay, you can twist left-handed or right-handed. So you can send circularly polarized light, and you can see the difference, in the absorption between left-handed and right-handed. And you can do all kinds of things to interrogate further, what the angle is and how large is it and what's the interaction between matter and light, etc.
Any other questions? Yes, right in the middle and then one on the side.
Expanding on a previous question, do you think if we could have one of these sheets, rotate or oscillate at some frequency, some attainable frequency, could we get something interesting out of it?
So very interesting question. I was discussing the other day with one of my postdocs who were trying to set up this quantum twisting microscope, that there are many modes to measure the properties, okay? In this quantum twisting microscope, you pass a current and you measure it as you rotate the angle. So then now when you pass a current, something which is very common in electronics is to do an oscillating current, to do this locking detection. As a matter of principle, you could do locking detection on the twisting, okay? If you send the frequency to your rotator and you oscillated it, and you could do do locking on the twisting as you rotate the angle, okay? We think that would be pretty cool. It's not the first thing that we would do, but it could be quite cool actually to look at that thing. Yeah. Because things can change dramatically with tiny angles. Less than 0.1 degrees can change dramatically the properties. So it can be quite cool, yeah, and very sensitive.
Question up here in the front.
In seeing that discovery of graphene in like 2004 with Scotch tape and then the Nobel Prize a few years later, like my reaction is like, why did that happen so late? I mean, someone could have got Scotch tape in 1970 and done that. Why do you think that was so late?
Very good question. Remember, there's a theorem that says that graphene should not exist. So if a mathematician comes and tells you, don't even try, it doesn't exist, most people say, okay, I will not try. Why am I going to try something that it doesn't exist? It took this, crazy, they're my friends, so I can call them crazy myself. So two Russians, to think, you know what? Somehow when you write this thing that you see, these traces, maybe if you do with Scotch tape and you do this thing, you will be able to get one layer. Why not? Turns out the conditions of the mathematical theorem are for infinite systems. So, well, maybe an infinite graphene sheet doesn't exist, but a finite size one does. They were also a little bit fortunate, in that graphene, you try to do the Scotch tape trick with many other layered materials, and they oxidize, they disintegrate, they suffer when exposed to atmosphere. But graphene is very inert, it's an ideal material to do this experiment. And the other thing is that it absorbs enough light that you can see it just with your bare eye, okay? So it was very easy to look with the optical microscope and find graphene flakes. Now, I'm making it sound like it's very easy. In hindsight, things always look easy, okay? But it took them a few years to develop all these techniques and the technology, even if it was simple, So, but I would say most of the hurdle was daring to try something which, if you ask any theorists, they would tell you it's impossible, it doesn't exist. And the urban legend, I haven't corroborated this with Andrea and Kostya, but the urban legend is that they sent first the paper to Nature, and the referees said, I don't believe it, there's a theorem that says this is forbidden, so this must be fake, And then, they did a bit more experiments, they sent it to Science, and Science published the paper in 2004, But the initial reaction from the referees was, this is impossible, so must be fake, So.
One more question in the back.
Sorry, let me add just one thing while the microphone gets there. After the discovery, a lot of people came and said, oh, you know what? I was once looking at the TEM in the 80s at a graphite piece and so on, and we saw this thing on the side, and it looked like a single layer, but blah, blah, blah. Afterwards, everybody started to claim that they had seen it before, but, that's afterwards,
Please, go ahead.
Yeah, maybe a different type of question. What's the future of possibly using these materials in battery technology?
Very good. I will speak a little bit about that tomorrow, okay? This, as I mentioned, we can realize all of the phases of matter that we know with these systems, okay? You want a ferroelectric, you want a ferromagnet, you want a superconductor, you want an insulator, you want You name it, I give it to you, okay? Now, I can give you one device, precious, students spent, 1 month making it. I cannot give you 1 billion of them all working at the same time, okay? So one of the biggest hurdles to make this into technology is that we don't know yet how to make scalable to Stronix, how to make even 100 of them in one, even 10 of them in one shot. We don't know how to do it, okay? I always tell people that my students, I mean, Sergio has heard about this, my students and postdocs are like medieval monks, they're making this manuscript, one precious, manuscript at a time. It takes a month and it's one of a kind, beautiful. But if you want another one, you have to start all over again, okay? We need to invent this thing called the quantum press, to make these things, much more boring in spirit, but much more practical, So if we were able to make these devices at scale, let's say 1 million at a time, magic angle twisted valley graphene is the thinnest, lightest, and least heat capacity superconductor that exists. You can make the world's best superconductor single photon detector for quantum applications or for space telescopes for astronomy that exists in the world. If we were able to make 1 million in one shot, all of them working reproducibly, we will be able to make cameras unlike the ones that we have now, much better, okay? Much, much better, much faster, much more sensitive. I will show tomorrow some data on hexagonal boron nitride, doing to Stronix with hexagonal boron nitride that allows you to do a special type of ferroelectrics, a new type of ferroelectrics called sliding ferroelectrics. These are the world's best ferroelectrics. If we could only make billions of them instead of one at a time, okay? So there are a lot of things like this where the properties can be intrinsically very good, but for industry you need, not only beautiful but also cheap and at scale. So that is among the obstacles that we're facing. Some of the properties are also very low temperature, so they have to be for niche, applications and quantum applications. But a few of them could, do work at room temperature, as the sliding ferroelectrics that I will show tomorrow. So I think it's mostly that it's very, very new. Okay, and I do have some sponsorship by by Samsung and some other companies and so who are interested in some of these things, but it's still, let's see how what these physicists are doing. The engineers are not yet fully on board.
Okay, I think we better end there. There'll be time for additional questions tomorrow. So let's please thank Professor Hariora once again.
Thank you very much. My name is Yong-Baek Kim, and it's not quite done yet. So it'll be very brief. Okay, so I promise. So my name is Yong-Baek Kim. I'm the chair of the Welsh Committee, and the Paul, our chairman, left an important task to me for acknowledging people who made this event possible. So first, I'd like to thank Welsh Committee members, Dick Peltier, Erika Rosenblum, Miriam Diamond, A.W. Pete, Hoi-Kang Lo, Peter Martin. And more importantly, this event was organized by many of our wonderful staff members, in particular, Helen Ayer. Unfortunately, she was not able to be here because she actually had an ankle fracture, unfortunately, but she made a lot of effort to make this happen. Also, we have support from Joanne Magnali and Eva Chung, she's standing here, and Jonathan Hooker and Julian Komanian. So all of them made important contributions here. And finally, I'd like to, of course, thank the two distinguished Welsh lecturers for giving this wonderful public talk. So just to show the appreciation, I'd like to present the frames of the posters here. So.